Hello, everybody. Come on in. I'm trying to see if my share screen is functioning still. I test it every day. Just be safe. Half the time it tells me I need to download a plugin, even though I've done that 1,000 times. Let's see what's happening. Looks like it's working now. All right. So does anybody have any questions before we get started?
Yeah, I had to I can't remember which one of the homework problems, but it was like determine the period for charge in the center of a ring if it's slightly offset.
Right. So with that, yeah, I think I know what you're talking about. With that one, what you need to refer to is let me see real quick. I think I have a copy of the book with that particular problem available for it. Yeah, let's go to the previous chapter. Let's go to 21. Should be okay, there it is. And with this, got more people coming in still, so hold on a second. Here it is. So let me see if I can share screen now. Share screen. Share. Of course, it's saying the same thing again. Let's try this. Now all of a sudden it's telling me it can't share. Okay, let me check this real quick. Turn off my Wi-Fi. And I'm going to stop share. Turn on my Wi-Fi. Try share screen again. I'm so glad it's so easy. This technology makes me feel much better. Yes, it mirrored that now. Woo, who's your daddy? Okay, got another person coming in. Now, what I was trying to share a screen with was this particular example right here. We actually worked this one out in class last time. It was like the first one we did with an integral. I don't know whether this is in my way, but it's making me angry. Okay, so we worked out this.
Remember that we got the detail, but we didn't get the period.
Yeah. So what you have to do is I'm actually pulling this so I could look up what the actual final answer was, and hopefully. Let's see if it's in this box right here. I haven't used this new version of the textbook in this new app until literally right now, so that's really making life a lot funner. Long line of charge, did that one. Uniformly charged disk. This is the one. Okay. So what we ultimately got was that the electric field. I don't want the disk. I want the darn ring. Where's the ring? The ring might have been next, maybe. The ring was before that. I think the ring was the first thing we did. Is this where you're working at? Ring of charge. Here you go. So this is the actual solution. The electric field is Qx over 4 pi epsilon naught x squared plus a squared to the 3/2 power. So what you're wanting to do is set up a differential equation with that electric field, I'm going to write that electric field over here because I'm going to use it in a second anyways. We found E, and I'm writing this on a piece of paper that y'all aren't needing to see, but I'm copying that last line just before it says number 4. So E is equal to Q times X, where X is the distance away from the center, over 4 pi epsilon naught, and then the bottom is x squared plus a squared, which I'll call x squared plus r squared because that was just the radius, and r makes a better variable for me. And that's to the 3/2 power. So what we have is the force is equal to the charge that is near the center times that. So you get Q times X over 4 pi epsilon x squared plus a squared to the 3/2 power. And that doesn't look very nice, but if you take the limit of X being very, very small compared to A, then you can basically say that that is independent of X. No, the bottom would be X cubed. No, the bottom would be a cubed, and then it'd be X. Okay, so that's proportional to X. All right, so let me let me explain what I'm saying. Now that I've got that written down, I'm going to back.
So the way that I was thinking about it was that there's a force that's pointing towards the origin of the circle, right?
Mm-hmm.
And as the particle gets closer and closer, the force gets smaller and smaller. And so you have a negative cosine curve for acceleration. And then I got lost.
Yeah, it's actually it's a little easier than that. Okay, so this is the force, and that's the only force that's going to be.
Ryan has a question.
Go ahead, Brian.
So everyone from the day class wants to be let in because they're waiting in the waiting room.
Gotcha. Thanks for letting me know. I'm
because I just invited them in.
Yeah, I'll admit them all in. There you go. There you go. I think I just did it all. I'm glad because I was wondering what was going on while we're getting some money, but then I remembered after you said that, Ryan. Thanks, bud. All right, if I see more come in, I'll do that. So yeah, that's the force, and then you got to use Newton's second law, which says the summation of the forces is equal to m d2x over dt squared. But here's the deal. Did I get another one come in? No, it didn't. Okay. When you set this up, you've got the mass of the charge times d2x over dt squared is equal to, we're going to take x being a slight distance away from the disk. In that case, this x cubed in the bottom is really, or x squared inside of a 3/2 power compared to r squared is essentially 0. So this force is going to become very close to q times x over 4 pi epsilon naught r cubed. Notice all of that is a constant except for x. So this is just like f equals kx. Not only that, if I set it up in a coordinate system appropriately, let's say the disk was right here and the x-axis is pointing out this way, and let's say the y-axis is pointing this way, and then of course the z-axis would be back into the page. If you displace a little charge q right here, that force is actually going to be acting in the negative x direction. So now you see that m d2x over dt squared plus, now here's the part that helps you, plus q over 4 pi epsilon naught r cubed times x is equal to 0. If you assume let x equal a e to the rho t, then x dot would be rho a e to the rho t, and x double dot, and dots, by the way, just mean derivative with respect to time. This one's going to be rho squared a e to the rho t. So you can plug all this back in and you'll get m times rho squared x plus q over 4 pi epsilon naught r cubed times x is equal to 0. But this has to be true at all times. Notice I just substituted the derivative in there in terms of the original x function. So if you do this, you'd say, okay, m rho squared plus q over 4 pi epsilon naught r cubed, all that times x is equal to 0. This has to be true for all time. So because of that, you can set rho squared plus q, notice I just divided through by the m, over 4 pi m epsilon 0 r cubed equal to 0, and that's times, yeah. So now you just got to solve for q and you get rho is equal to, or excuse me, solve for rho, not q. Rho is equal to plus or minus I times the square root of q over 4 pi epsilon naught r cubed. So if you remember from your harmonic oscillator, the harmonic oscillator had m, actually, excuse me, m d2x over dt squared equals negative kx. And that gave us d2x over dt squared plus k over m x is equal to 0. And this became omega squared. That's the frequency that it oscillates with. But omega is equal to 2 pi times the frequency. And the frequency is 1 over the period. So omega is equal to 2 pi over the period, or t is equal to 2 pi over omega. So whatever goes in front of that x plays the role of omega squared. So in our case, what went in front of that x was essentially the q over 4 pi m epsilon 0 r cubed. So for us, oh, I don't know what I did there. Oh, I had it on screen. For us, omega will equal the square root of q over 4 pi epsilon naught m r cubed, which equals 2 pi over t. So t is going to equal 2 pi times 4 pi epsilon naught m r cubed over q times q. So that's the period. See how they're pulling something that you did for like a hot second in chapter 14/15? That's the way physics sort of works. It continuously checks you on the things that you supposedly already knew, even if they were from a whole course, you know, back in the past, 3 years ago. They expect you to know every bit of math and every bit of science that you've learned since kindergarten, essentially. So I apologize for that, but I'll tell you, that's how they did it. And whenever they ask you for something like that, what's a period, or what's a frequency, or what's the angular frequency, any of those rotational variables, what they're expecting you to do is set up a simple harmonic oscillator equation. The simple harmonic oscillator equation is always m d2x over dt squared equals negative kx And there might even be a term minus b dx dt. Okay. Other than that, then that's basically how they're trying to do that every time. So does that help you with that particular problem? It's a
Yeah, I think so. I'm gonna have to go review the A E rho T thing, but yeah.
Yeah, another way, actually look at your book. That's just the way I remember from my differential equations class. So if anybody was taking differential equations, I showed you that way. What your book does is your book will say x is equal to a cosine kx minus omega t or something like that. And you can do it that
Yeah, I
way.
remember that.
Yeah, if you plug that in, that might make a little more sense to you.
What I did was I solved, for the force of the electric field, and I set that equal to kx.
Right.
And I found out what k was, and then I did that.
That's exactly right. Then you could just treat k like m times the square root of omega or whatever it is. Because remember, omega is supposed to be the square root of k over m. So if you solve that, that would be omega squared is equal to k over m. So m times omega squared would be k. Yeah, so you do it that way and then solve for omega. And then, of course, you just have to remember how omega relates to the period. They almost always ask you a period, which is the hardest thing to do. If they ask you for omega, it's easy peasy because you just take it right off the differential equation. But no, of course, they're going to ask you for the t. Does that make sense to everyone?
Not really, but I just got here.
Okay. And actually, that's an honest answer, but that's also a useful answer. What I mean by that is absolutely what I not have expected you to remember that. If I gave you that on a test, on your first test, and I'd never given that homework a problem, I would be a bad instructor. Now, what the point is you've now done a homework problem and you said, oh yeah, I remember we did that in chapter 14. You go back and look at chapter 14, that's going to make a lot more sense. And then if I ask you on a test, I'm actually being a fair instructor. So
Fair enough.
it's perfectly reasonable for you to not understand it right now. But assuming you got into chapter 14 in your 241 class, I don't know if you had me or not. I know Ryan had me, and several other people had me. But if you didn't have me, you might not even have done chapter 14, or you might have skipped that part. But that's all what chapter 14 is about, to see all the different ways that things look just like harmonic oscillators. That's why we study springs so much. It's not because we got some fascination with springs, and it's not because springs are the really easiest problems to solve. It's because everything looks like a spring in some way or another. In my class, I showed everybody how if you did a Taylor series expansion of a potential energy, one of the terms came out to be a constant times x squared. And that's actually the term that is just like a harmonic oscillator. 1/2 kx squared is a harmonic oscillator. So when you're dealing with a equilibrium problem where it's near the equilibrium but maybe slightly off, then you automatically have a harmonic oscillator. That's why atoms behave like they're connected by springs and all that stuff. So it's really is a big thing to learn. How about anybody else? Anybody else have any questions on homework?
I would like to talk to you after classes. I did the extra credit for the second one, and I was learning to see
Gotcha.
if
That's not a problem, Ryan. Anybody else?
I actually wanted to ask you, you had mentioned extra credit while we were on the last lecture,
Right.
and I was wondering how to turn that in.
Let me show you here. Hopefully it works. I'm going to share my screen again because, I'm so awesome at doing that. I just feel like I've got a superpower now. So, so it's not here in the Zoom, it's in the modules. And I'm assuming it's this class 242. So down here in the homework section, if I did everything properly, you should be able to go to week 1. And was this the homework problem you were talking about? You'll see it when it pops up in a second. In class, we worked a problem like the one in the textbook, only made the distances this. Is that the one you're talking about? Nathan? I think it was Nathan.
Yes, I think so.
Okay, so somewhere here, it's supposed to allow you to turn it in because it says it only takes a file type PDF. So I know it's doing that right now. Because I'm the instructor, I have no idea where to crap turn it in. But What does this look like from y'all side? Anybody from the class? Maybe if it's up here.
I'm
Share
checking
it.
right now.
For me, it has a start assignment button, and when you click start assignment, it
Gotcha.
pops up the choose the file, make sure it's a PDF, and you can submit it that way.
There you go. Thank you. So yeah, it doesn't look like that for me on this side, as you can tell. So I always require PDF. So what that means is write it up by hand, take a photograph of it, take a Word document, either put the margins to narrow or none, and then just insert that photo in the Word document, save it as a PDF, and turn it in there. Sorry for the rigmarole. It's just we're a lot less likely to pick up any viruses when you're handing in PDFs than when you're handing in anything that Bill Gates made. No
One
disrespect to
more,
Bill Gates. Go ahead, Ashley.
the Pearson. I'm still working with the free trial because I'm still having issues getting it to actually credit over, but I did the conceptual and the homework and stuff like that, but it still doesn't say anything on Canvas has been completed. And I don't know if that's just a waiting for it to credit over kind of thing, or if I am now late because I needed to do it off of Canvas.
Well, since
first,
I'm not
or-
sharing, let me check that right quick.
I think that's just because there's a difference between my lab and Canvas. I also did the homework with the free trial, and I know I completed it. So I'm guessing it's probably just
Yeah, sometimes
communications.
it takes till after midnight for it to load up, but I'm checking right now to see who was that was answering. Was that Trey? Or I'm sorry, I know I'm
Yep.
horribly
Howdy.
your name. I
Yeah, I
recognize your
had the
voice.
same issue.
Hello.
I had the
Yeah, I
same
did it
issue.
days ago, not
Because Mr.
not
Younger
like
trying to
last
pronounce
night,
words
but it was
again.
done days ago.
So I'm looking in that grade book, and it looks like you're all failing. None of you done anything. I don't like you at all. No. It actually does look like that's got nothing but gray marks. Okay. No, it's got some extra credits turned in. Okay, yeah, so it's being a jerk. That's not y'all. That's probably something on their side, which let me check real quick. There's a place where I go, I hit my lab and mastering, and it allows me to sync grades. And it's set on all. Nope, it's not set on auto. There's why. And they should appear by midnight tonight now.
Okay, thank you.
No problem. And now let's check back at my other students. They're over here. I'm going to check yours. Those of you, my nighttime students. I missed class yesterday. That's where my daytime students are here as well. Yeah, we're covering the same material at the same rate, so it normally works pretty well. I just invited them here optionally. I am checking to see if yours is updating. Has anybody from this night class seen their homeworks in the grade book?
I did it and I have not seen it in the gradebook in Canvas.
Okay, mine is set to automatic sync correctly on this case. However, it has for some reason chosen to not select any of the homeworks. It's just acting like, yeah, well, we'll do that, but we're not going to do it to any particular assignments. We're just going to have this little button like, so that should update, excuse me, tonight as well. All right, I got that done. Okay, so I think I've gotten all the homework questions done. We finished essentially chapter 21. There was a couple things I wanted to show you. Basically, what I wanted to do is show you another way to find the electric field of a continuous charge distribution. And it happened to be in a case where I was going to use that result that I just copied down. So let me share my screen. I'll do that. Then I will make a quick rough derivation of the momentum, of the torque applied to a dipole. I'm going to redefine a dipole for you, electric dipole, and then calculate the dipole torque, or the torque on the dipole when it's in electric field, and calculate the the potential energy when it's in electric field. I don't know why I just pushed the button that I did do, but here I am. So I've got now share this. What we want to do now is we want to calculate the electric field at some distance above the center of a circular disc. So what I'm going to do is draw a circular disc like this, and it's going to have a radius, say, R. I'm going to put a coordinate system conveniently like this, and I'm going to say the point in question is going to be right there, and it's a distance Z up. This is going to be my x-axis, this is going to be my y-axis, and this is going to be my z-axis. And I'm going to say the charge on this thing is uniform so that sigma is equal to Q over pi R squared. That means I have the freedom of referring to sigma, the charge per unit area, or Q, the total charge, whichever one, it doesn't matter. Now, what I do know is that I found the electric field for a ring of charge like this guy. I found the electric charge for that, call it dE, and that's going to be equal to x dq over 4 pi epsilon naught. And now I'm going to say that's the distance z squared away plus r squared to the 3/2. Okay, that's, in other words, I'm treating this ring of charge that we solved earlier as a problem by itself. I'm pretending like that ring of charge is now my differential charge element, and I'm going to integrate that instead. So what I would say, and my daytime students have seen this already, so don't feel like you're in a deja vu moment or something. It's okay. You are. You are. So this little green bit of charge is going to be called dq, and it happens to be, it's weird the way this works out, but it's going to be 2 pi r dr times sigma. Okay, in other words, it's really pi parenthesis r plus dr squared minus pi r squared, because the radius is to there and the width is dr. Right? That's mathematically what that differential area element is. But if you actually work that out, you'll find out that that is essentially 2 pi r dr, except for terms that are like dr squared or dr cubed. So if you work out the details, you'll see that that's acceptable. And that's why we use that as our differential charge element. It's just sigma times dA. So now I'm going to say E is equal to the integral of dE, and I'm going to try to stop laying my fat arm on my keyboard. So
Should the variable in dE be a z instead of an x?
Yes, thank you. Because we had done that before in the x, but yes, I will change that in the integral. So I'll write a note here to that just to remind us. Okay, so now what I'm going to do is I'm going to write the integral. Evidently, I'm going to change colors too. I'm going to write the integral of z times 2 pi r times sigma dr over 4 pi epsilon naught. I just realized that I had changed it to z in the bottom, but not in the top. So, oh well. So this would be z squared plus r squared to the 3/2 right there. And I'm going to integrate it from r equals 0 to r equals big R. Now you can see the Z, the 2 pi, the sigma, the 4 pi epsilon naught, all that is just constants. So I'm going to pull that out in front and I'm going to say 2 pi Z sigma over 4 pi epsilon naught is the constants, or are the constants. And then I'm going to say what's left inside is RDR over Z squared plus R squared to the 3/2. Now this might look bad, like you're thinking trig substitution, but because I have that RDR up there, this makes it quite easy. So I can say, let U equal Z squared plus R squared, then DU is equal to 2RDR. So I've already got half of DU in the top. So I need to multiply that by 2 and then divide by 2. So you can already see this guy was canceling out with that and leaving a 2. But now I'm going to multiply by 2 to get the DU up there and then divide by 2. So now I'm going to have, back to the green, pi Z sigma over 4 pi epsilon naught. I could have canceled out that Z as well. Let me do, I mean that pi as well. Let me do that now. And now I'll go back to my green. I'm going to say the integral of du over u to the 3/2. So that's just an integral of u to the negative 3/2. And when you take u to the negative 3/2 and you add 2/2 to it, you get negative 1/2 divided by negative 1/2, which is the same thing as multiplying by negative 2. So I'm now going to get negative 2 Z sigma. Isn't that convenient that that 2 looks like so much like a Z over 4 epsilon naught. Now I have, I've already taken care of the one that. So all I need now is I'm going to take Z squared plus R squared. Actually, I just write it as a square root in the bottom. And I'm going to evaluate that from R equals 0 to R. This gives me negative sigma Z over 2 epsilon naught. Now, when I evaluate the R, I get 1 over the square root Z squared plus R squared minus, when I evaluate the R equals 0, I get basically 1 over the absolute value of Z. So I'm going to flip the order of that and get make it equal to, and I'm also going to distribute the Z through. I'm going to say now that I have positive sigma over 2 epsilon naught times 1 minus Z over the square root of Z squared plus R squared under the square root. And that is my actual electric field. And that's just along the axis, but we can do it like this, put a vector symbol over there and put a K hat here. And now we've determined the actual electric field above a disk. Now, if you consider Z much less than R, then what happens is the plate starts to look like an infinitely large plate, right? So Z much less than R ends up becoming just a 1 minus 0, because this Z squared added to R squared just becomes R in the square root. And then you let R approach infinity, basically. So 1 over R as R approaches infinity, 0. Then you end up getting E going to sigma over 2 epsilon naught, which you'll find out later is exactly the right response when you're close to a plane or a disk. Any questions on that? So notice this was a lot easier integral than that infinite straight line. It was even easier than, well, it probably wasn't easier than the circular ring, but anyways, it was definitely easier than that infinite line. Does anybody have any questions on how that was done? Remember, this video will be posted tonight. It usually takes a couple hours for it to it converts it to the MPEG, and then I post it to my YouTube channel. Sometimes I go and watch TV for a second and then I forget, and then I don't put it up till 11. But in principle, it should be done within a couple hours after class. But if we don't have any questions on this, I'm going to go ahead and do the two dipole things, refresh your memory what a dipole is, and then I'm going to jump into 22, which is a really, really short chapter. So here goes. All right. So if you have a positive charge, Q, and a negative charge, negative Q, and they're separated by some distance, D, they're equal in magnitude but opposite in charge, then we have what's called a electric dipole. So in fact, what you can do is you can imagine a vector that points from the negative charge to the positive charge and whose length is D. This will be the D vector. And then there's a vector P called the dipole moment. And that is equal to Q times the vector D. Notice the vector D points from the negative charge to the positive charge. Now, if I submerge this dipole in a uniform electric field, then I could, for instance, say, here's the positive, here's the negative. There's the vector D, okay? And I think what you'd see is this D vector here acts like a lever arm. If you imagine the center being, say, right about there, then you'd say the torque on the positive one should equal D over 2 times the force, which is Q, times the electric field, which I'm going to say is E. And that actually tends to rotate it in a clockwise direction. Similarly, I think you'll see that the torque on the negative one would also equal D over 2. Actually, I'm leaving off a little bit of details here. I'll leave that blank. Q times E, and that 2 is tending to rotate it in a in a clockwise manner. Does that make sense to everybody? Does the torque look like it's tending to rotate this way and this way? Now remember, torque is R times the perpendicular component of the force, or you can say it's the perpendicular component of the R times the force. What we know for sure is the force is parallel to E. So if we took and only took the component of E that is perpendicular to D, then this would be E perp. And in fact, if we called this the angle theta, actually you're supposed to technically put it tail to tail. So if you call this the angle theta, that's really what we're talking about. But I think you can see the sine is what's going to give us the actual component perpendicular. So what actually goes here is the sine theta. and the sine theta. Now,
Oh,
if you
went
remember from
silent
your,
for everyone, right?
what's that now? What'd you say, Ryan? Or Nathan, whoever that was?
Oh, yeah, my connection went off.
Okay. So since both of those are d over 2 QE sine theta, I think you recognize from vector algebra that when you have two vectors times a sine of theta, that usually means a cross product. And torque is meant to be a cross product. In fact, we've already said torque is equal to R cross F. That's one of our definitions of torque. So in this case, we find that torque is equal to P cross E. Because what happens is the d over 2 and the d over 2 add together to just give you d times q times e times the sine of theta. So that is in fact a cross product. Similarly, if you took u equal to the work done in rotating it, that equals the integral of torque d theta. If you carried out that process, what you'd find is negative p dot e is the potential energy. So we'd say U is equal to negative P dot E, like that. And that's our other relationship for dipoles. Okay. What it's telling you, though, is that there's a potential energy that you can minimize when the orientation of the dipole is in a certain way. Since it's the cross product, this number is going to get a maximum negative number, which is when U is the smallest, specifically at cosine theta equals 0. And that's, of course, cosine theta equals 1. And that's, of course, when theta equals 0. So when the positive end of the dipole is pointing in the positive direction of electric field and the negative end is in the opposite direction, that's when it's sitting at rest in what we call stable equilibrium. When you flip it 90 degrees, it's again at rest, but it's not a stable equilibrium. If you just give it a little punch one way or the other, it's going to flip around. So those tell you why magnetic or why dipoles behave the way they do in electric fields. And one of the big ones, like I told you before, is the water molecule, which looks like Mickey Mouse. And the water molecule has the oxygen that actually becomes like a noble gas when it steals those 2 electrons. So it holds on to those 2 electrons really well. And the hydrogen, of course, holds on to the positive side really well. So this actually acts like an electric dipole, like that. So if you subject this to, for instance, an electric field, it's going to rotate. Not only that, it turns out you can make a magnetic field too. And that's what happens when you do use an MRI, for instance, is that magnetic field can flip. When it does, it causes water and other elements and compounds, molecules to flip back and forth, back and forth. Each of those flips is associated with a certain amount of energy. That amount of energy is associated with a certain frequency or a certain wavelength of radiation. And then you can tell what elements are present when you're doing the MRI. Of course, that's with a magnetic dipole, but there's a similar analogy for electric dipoles. So anyways, anybody have any questions on those dipoles? That's mostly just something for you to calculate, using either cross products or dot products, forming vectors out of charges and the distance between them, and creating coordinate systems to use, that sort of thing. So now that we've done that, we can introduce you to chapter 22, which is really the crux of tonight. And that gives us, we're supposed to run till 6:40. So it gives me about 36 minutes, which is actually plenty of time, believe it or not. The reason why chapter 22 is so short is chapter 22 covers something, a lot of which we've already done in chapter 21, and then a lot of which we'll keep on doing in chapter 23 and 24 and 25. So that's why they sort of sell it short. And the chapter's on Gauss's law. So let's say chapter 22. Again, I don't remember exactly the name that the author chose for it, but I think it was just Gauss's law. So what Gauss discovered was one way of looking at it's a differential equation. Another way of looking at it is a integral equation. I will later give you the differential equation, but right now we're going to work with the integral equation. But to do so, we first have to talk about something called electric flux. So electric flux is given the symbol of the Green Lantern. No, that's actually phi from the Greek alphabet, but it looks like the Green Lantern, right? So anyways, in its most rigorous form, it is an integral of E dotted with dA. What do I mean by that? Well, that looks pretty crazy. For starters, you're dealing with an integral that has a dot product in it. That's something that most people haven't seen unless they've had Calc 3. But all we really mean is if the electric field was uniform, this flux can get a lot simpler. So let me show you how simple this flux can be in the case of a uniform electric field. So let's say we have an electric field that looks like this. And let's say we imagine a little bit of surface that looks like this. Okay. So that surface has an area A, and we can represent this surface by a vector perpendicular to it because it's a flat surface. So we can represent that vector, or excuse me, that surface by a vector A like that. And notice the criteria is that A is actually perpendicular to that surface. Now, being a surface like that, it's somewhat arbitrary. I could have, for instance, said A vector points that way, and that would be acceptable as well. Later, when we start doing Gauss's law, we're only going to allow closed surfaces that have a clear inside and outside. And when you do that, that takes that ambiguity away because we could just say we're going to define the A vector to point out. So right now, we don't have that concreteness. I'm going to draw a couple more electric field lines just to let us see what we're talking about here. And what you'd see is right here, you have an angle theta. Notice the vector E and the vector A are tail to tail. That's the way we define our thetas and dot products and cross products and that sort of thing, is when they're tail to tail. So in this case, the actual flux would just be E times A times the cosine of theta. So when I write it in integral form like that, what I'm meaning is what happens if the electric field changes? Well, if the electric field changes over space, then I might have to find this A and break it up into little differential area elements, dA, so small that the electric field doesn't change very much over that, and then take the dot product of that electric field with that itty bitty dA, and then add up all those itty bitty E dot dAs to get the actual total flux. So for instance, if we had a surface like this with an electric field that was doing this kind of crap, things could get hairy. So for instance, right here, we might say, well, there's my dA, and over that area, the electric field doesn't change too much. So I could do that little part, and then I have to sum all of them up. So that's really what we're doing by writing it as an integral form. Okay, so that's what electric flux is. If for instance, if in this problem, E is equal to 100 newtons per coulomb, And let's say A is equal to 2 meters times 3 meters, which is 6 square meters, and theta equals 30 degrees, then phi would be equal to 100 newtons per coulomb times 6 meters squared times cosine 30 degrees. Doing my special triangle over here. Here's the 60, that's opposite the square root of 3. Here's the 30, that's opposite 1. And here's 2 over here. So the cosine of 30 is root 3 over 2, which is 0.866. So this is 600 times 0.866. And I get 519.6. Notice the units, they're Newton meter squared per coulomb. So that's a simple example of calculating the flux. Okay. Now, in general, you'll be calculating fluxes over closed surfaces to do Gauss's law. And all it means is you've got to evaluate, when you're doing what we call a surface integral, you've got to evaluate the integrand on the surface of the closed surface. So for instance, if you had a rectangular cube, not a solid, but a rectangular set of plates like this, and you had some electric field as a function of X, Y, and Z, you'd have a left plate, a right plate, a top plate, a bottom plate, a front plate, and a back plate. And the back plate might have X equals 0, and the front plate might have X equals 4. But Y and Z can change on both of those. So what you do is you take your E as a function of X, Y, and Z, and when you're integrating over the back face, then you're going to substitute X equals 0 for it. But when you're doing the front face, you're going to take your E as a function of X, Y, and Z, and you're going to let the X be 4 meters. And then you've got to find, of course, little differential area elements, which have to be perpendicular to the surface. So for that side, it's this one. For that side, it's this one. For this, it's this one. For that, it's that one. For that, it's that one. For that, it's that one. Okay. Notice how it being a closed surface, there's no ambiguity about which direction the dA vectors point. The dA vectors have to point from the inside towards the outside, and they have to be perpendicular to the surface. So that's dA right. This is dA left. This is dA top. This is dA bottom. This is dA. I'm going to say back, but I've already used B. So I'll say I've already used right as well. Let's say DAA for the tail end. I guess I could say DAT for the tail end. And then DA front. Crap. Yeah, I'm going to say tail then. So I don't have to bring in a cuss word.
So electric flux is basically sort of the amount of electric field, I guess, that's going through area at a time, or am I missing
Exactly.
something? Okay.
Yeah, it's sort of like the amount of sunlight that makes it through your windshield to actually fade your car seats or coats or
Okay.
paper that's written through there. The only parts that count are the parts that are coming perpendicular to the window, because the parts that are running parallel to the window are just going to be absorbed by the window and heated up.
Yeah. Okay. For anyone, by the way, who has not done differential equations yet, is wondering why we're doing vectors that are perpendicular, think of it sort of like you're throwing a baseball up as far as you can to see how far horizontally it'll go. That sort of helps you with the whole, then you can learn the real mathematics behind it and whatnot.
Yeah, when you're using planes, the vector perpendicular is the only thing that's fairly unambiguous with regards to the plane.
Yeah.
So-
Also, it's much easier to write.
Exactly. Yes. So there you go. So that's actually how, if I were to ask you to calculate a flux, and you'll see on my YouTube channel, I've done some of these where I've just taken arbitrary electric fields and arbitrary rectangular shapes, and I broke them down into the 6 surfaces. And on those surfaces, I evaluated X, Y, and Z, and the electric field and dA for each of those 6 surfaces, and then integrated all of them. So in this case, you'd be doing the closed integral of E dot dA, and that circle around the integral just means, hey, this is reserved for closed surfaces. That means surfaces that have a definite inside and outside. That's what the circle around the integral is. Now that we have some sense of what Gauss's law is, I'm going to say now Gauss's law is that the flux is equal to Q enclosed over epsilon naught, where that epsilon naught's the same 8.85 times 10 to the negative 12th Coulomb squared per Newton meter squared that we've been doing. And the Q enclosed means any charge enclosed inside of the Gaussian surface. So the left-hand side is the flux, but I can write now the closed integral of E dot dA. And that right there is one of the normal ways, even though I wrote it backwards, that's one of the normal ways to write Gauss's law. So let me show you the power of that. Okay. So this is Gauss's law. I was telling my 202 class this morning, this is Gauss's law, not Gauss's helpful hint that sometimes works. It's Gauss's law. It's always true. The problem is what we're doing with Gauss's law is usually taking that integral equation and using the physics and the symmetry of the problem to derive the electric field inside of that integral. That only can be done in certain highly symmetric situations. That's why it seems like it's not always true. No, it's always true. It's just when you're trying to use it in that very special way, that's the only way it can be used that way, is when there's certain symmetries. And the symmetries are spherical, cylindrical, and I mean infinitely large, and planar, again, infinitely large. Okay, so let me show you our first example. Let's imagine that I have a spherical charge Q at the origin. So a spherical Q is centered at the origin. Use the closed integral of E dot dA equals Q enclosed over epsilon naught to compute the E field it creates. Okay, so that's the problem. This is going to be my x-axis, this is going to be my y-axis, and this is going to be my z-axis. What I'm going to do is I'm going to realize that the electric field, due to this spherical charge, since it's uniformly distributed over the charge, and that's spherical, we know the electric field is going to have spherical symmetry. In other words, it's always going to point radially outward from the origin. So my electric field lines will be like this, this, this. And in fact, at a given distance away, it'll always have the same magnitude. So if I went 3 meters away in any direction, the magnitude of it would be exactly the same in any other direction. So what I'm going to do is I'll realize, hey, if I choose a Gaussian surface that's a concentric sphere, then the electric field on that spherical surface will be a constant, and it's going to be pointing radially outward. In other words, it's going to be parallel to that dA vector. So what I'm going to do is I'm going to create a Gaussian surface that is a concentric sphere. Okay. So for that dA, and here's where I'm going to make use of spherical coordinates. dA is just going to be some dA r hat. Some people use rho for the radial coordinate and spherical coordinates. Others use r. I'm using r. And the dA technically would be, if you really wanted to know it, it would be r cosine theta d theta times r d phi. So r squared cosine theta d theta d phi. So if you actually did that, then that would actually be dA. We're not going to have to do any of that. I'm just using the symbols from spherical coordinates, so I don't have to think about, you know, what I'm going to name it or anything like that. Now I can also say from symmetry, E should be equal to E only as a function of R, and that should point in the R hat direction. So that's my hypothesis. So now I'm going to write, I'll say all this is the solution. Okay, so I've got my hypothesis. I'm going to say left-hand side of Gauss's law is the closed integral of E dot dA. Well, E, we already said, was E of R hat dotted with dA, and dA we said was dA R hat. Well, the dot product's what we call a linear operator. What that means is the dot product acts on vectors, and scalars can just go right through it with no change whatsoever. So I'm going to write this now as integral E of R dA times R hat dot R hat. Anybody recall what the hats mean on vectors?
Unit vector.
It's a unit vector, so its length is 1.
Still my answer.
What's that?
Still my answer, Ryan.
Okay. And then remember, dot product is the magnitude of one times the magnitude of the other times the cosine of the angle between them. Since the two vectors are identical, what's the angle between them? Yep, 0. So cosine of 0 is 1. So I get 1 times 1 times 1. So this whole r dot r just becomes 1. That's mathematically what's going on. And that's what's supposed to happen sort of mathematically every time, is you're going to get 1 or you're going to get 0. And you should know where the 1 occurs and where the 0 occurs, but eventually you'll get where you don't even have to think about it. Now, because we're doing it on the surface of the sphere, we know E of R is in fact E evaluated at the radius of the sphere R, and therefore it's a constant. So we get E of R times the integral of dA, which really just means the surface area of a sphere. So I'm going to say that's E of R times 4 pi r squared. So that's the right-hand side. Or excuse me, the left-hand side. The right-hand side, on the other hand, is Q enclosed over epsilon naught, which is really, really easy. We know it's just Q over epsilon naught. So left-hand side equals right-hand side gives me E of R times 4 pi r squared is equal to Q over epsilon naught. So I've got E, using my original hypothesis, is equal to Q
over 4 pi epsilon naught r squared pointing in the r direction. And that's exactly what we found from Coulomb's law. Does that make sense?
What if you did it with a cube instead of a sphere?
The right-hand side would still be Q enclosed over epsilon naught, and which is the total flux. But the problem was you would ultimately end up doing a lot of complicated integrals because you'd have the DAs always pointing up, down, left, right, back, or forward, and the E would have always be radially outward. So you'd have to be taking dot products on each of them. It's really ugly. And in fact, all of electricity and magnetism is horribly ugly if you start talking about cubes and rectangles and stuff like that. We like spheres, we like infinitely long cylinders, and we like planes. That's the best of the world for us. So Coulomb's law Gauss's law would still be true. It just wouldn't be helpful for us to try to find the electric field by using that Gaussian surface.
Yeah, they had a problem in the book where they wanted us to find Q if given the electric flux. And I was like, how would I even do this?
Yeah, that's actually a reasonable problem, depending on how they word it. If there's no charge inside of it, then you know the flux is going to be zero, period. Or if you have a charge of 2Q and a charge of negative Q and another charge of negative Q, the total flux or the total charge inside of it zero. So again, the electric flux would be zero. So there's a lot of ways they can make that easy.
They gave us like a side of one side of the cube, and I was like, I think it definitely, yeah.
Let me show you one that's kind of neat, and this might be related. If I were to take a charge right here and say it is 4.0 microcoulombs, and I put it at the corner of a cube that looks like this, and I'd ask you what is the flux through this surface right here, that looks like an impossible problem until you say, well, let's imagine it was actually inside of a cube like this. And then, of course, you have to do the same thing back here. So then all of a sudden you say, oh, okay, well, this surface right here is 1/4 of this surface back here. And that should be basically 1 microcoulomb, or excuse me, 4/6, or excuse me, 4/6 of a microcoulomb per E. So this is 1/4 of 4/6 of a microcoulomb over epsilon naught. Because it was on the corner of that little red cube, you can make that the center of a more bigger or a more big cube. And then by symmetry, the exact same amount will have to go through every face. You've got 6 faces. The total flux coming out of that has to be 4 microcoulombs over epsilon 0. That means each face gets 4 microcoulombs over 6 times epsilon 0 in the bottom. And then, of course, that little cube that I colored in blue, that little face is only 1/4 of that whole face. So I multiply that by 1/4. So I should get about 1/6 of a microcoulomb per epsilon 0 out of that little red encircled blue face. Does that make sense?
Yeah, now it does. I was like,
Yeah, that's a little
Because
bit it's an ingenious way of doing it, but that's the kind of tricks you can pull with Gauss's law.
the
All right.
symmetry.
Yeah, let me show you. Remember the first day, the worst problem we did was that infinite line of charge, right? Well, check this out. I'm going to draw my coordinate axis like this. and I'm going to say, hey, I got a uniformly charged, infinitely long line that has a charge per unit length lambda, but it goes on for infinity. And again, in physics, all that means is if you're 10 centimeters away from the center of the wire, then as long as the two ends are at least 100 centimeters away, but preferably 1,000 centimeters away, then you're probably close enough to being infinitely close. In other words, you're pretty close to being an infinitely large wire. So that's all that means. Now, what we're going to do is we're going to use Gauss's law to find E. So my hypothesis is, actually, I should go ahead and change to a different color. I'm going to make my solution be in green. So what I'm going to do is I'm going to draw a Gaussian surface. Since I know that the electric field lines will point radially outward from this wire. And what I mean by radially outward is they're going to only have X and Y components. They're not going to have any Z components, right? So I'm going to imagine a soup can whose length is L and whose radius is R, and that's going to be my Gaussian surface. Now, here you can see what the dA will be. It'll be a little guy like that. And I call this the dA for the soup label. And what that really is R d theta dz pointing in the R hat. So I'm using cylindrical coordinates this time. Again, all I'm using it for is so that you have some familiarity with the variables and the symbols I'm using. You don't really have to do any of the calculus with it, okay? But it has to be a closed surface, so we're also going to have a dA for the lid. And this is what the dA looks like for the lid. So the dA for the top is going to equal R d theta dr, but that's going to point in the k hat direction. And the dA for the bottom is going to be R d theta dr k hat, but that's going to point in the negative direction. That makes sense? So my hypothesis is that E is equal to E of R in the R hat direction. This is E of R of the cylindrical coordinates that are not E of R of the spherical coordinates, so it's different, all right? So then the left-hand side of Gauss's law is the closed integral of E dot dA is equal to the integral of E of R, R hat, dot dA top plus integral E of R, R hat, dot dA bottom plus integral E of R, R hat, dot dA soup label. Okay. Now, for the top one, what we get is the integral of E of R, R hat, dotted with the dA for the top was R d theta, R d theta, K hat. You can see that R hat dot K hat is going to give you 0. Not only that, that's lucky because this R would actually change from 0 to R and it wouldn't be a constant. So we couldn't really work out stuff, but luckily the R hat dot K hat gave us 0. So that one goes to 0. The bottom one, whoa. We got the integral of E of R hat dotted with negative R d theta K hat. Again, this is a linear operator, so we're only going to get R hat dot K hat with a bunch of crap in front of it, but that's 0. So the whole left-hand side just becomes integral of E of R hat dotted with R d theta dz R hat. Well, technically you could go ahead and do that integral because I gave you all the details, but really that's a double integral. We don't have to do it. In fact, since we're doing it on the soup label, the R is a constant. It happens to be the radius of the Gaussian surface. So I've got E of R coming out in front, and then all I have is the integral of dA, because the R hat dot R hat was equal to 1 again. And of course, the area of the soup label is just 2 pi R times L. Right? 2 pi R is the distance around. So if you were to cut a soup label off a can of soup, its length would be 2 pi R, but its height would be L. So it's 2 pi R times L. That means the right-hand side, which is Q enclosed over epsilon naught, has got to equal lambda L over epsilon naught, right? Because lambda is the charge per unit length, and the length that I chose was L. So left-hand side equals right-hand side gives me E of R times 2 pi R L is equal to lambda L over epsilon naught, or E is equal to lambda over 2 pi epsilon naught R in the R hat direction, which is, by the way, exactly what we got when we did it with Coulomb's law in integral form. Now, I would ask for questions, but I want to do one more surface for you real quick. So let me do an infinite plane. This goes on for infinity that way, goes on for infinity that way, goes on for infinity this way, goes on for infinity this way. Okay, got 2 minutes left. It has a uniform charge density, charge per unit area, sigma. So what I'm going to do is find E using Gauss. Now, because this is an infinitely large plane, I expect above the XY plane, I expect the electric field to be pointing up. And then below the XY plane, I expect the electric field to be pointing down. So I'm going to say my hypothesis is E is equal to E of Z K hat for Z greater than 0 and negative E of Z K hat for Z less than 0. Okay. Now I'm going to choose my Gaussian surface as a soup can again, or a pill bottle. Like that. Okay. This has a dA top. This has a dA bottom. And this has a dA soup label. Okay. I'm going to say dA top is actually equal to dA K hat. dA bottom is actually equal to negative dA k hat, and dA soup label is actually going to be equal to dA, and then I'm going to say n hat as a function of x and y, because it's only going to be pointing in the xy plane. There's going to have no z component whatsoever. So I'm just using a made up vector that I know n means normal, so it's normal to the surface. So now the left-hand side of Gauss's law is the closed integral of E dot dA. Well, that's equal to the integral of E of z k hat dotted with dA k hat. That's for the top. Plus the negative E of z k hat dotted with negative dA k hat. That's for the bottom. Plus the integral of E of z k hat dotted with dA n of x and y. Okay. Now k hat, whoa, why did I switch to that all of a sudden? So k hat dotted with dA, excuse me, n hat is equal to 0, because the n hat only has x and y components and the k hat's only a z component. So the left-hand side ends up equaling E of z times A, where I'm calling this area A, and I'm calling this area down here A, plus E of z times A, which equals 2A times E of z. Does that make sense to everyone? All right, let me do the right-hand side, which is supposed to be really easy. Right-hand side, it's Q enclosed over epsilon naught. Well, the Q enclosed is just going to be sigma times A. So I got that. Now, if I say left-hand side equals right-hand side, times up for the class, you are, of course, free to go. You can catch the end of this recording if you have to leave. I'm going to go ahead and write 2A E of Z is equal to sigma A over epsilon naught, which I think you'll see ultimately turns out to be E is equal to sigma over 2 epsilon naught k hat for Z greater than 0, and sigma over 2 epsilon naught k hat negative. Let me fix this real quick. For Z less than 0. And in fact, what you notice here is there is a discontinuity in the electric field equal to exactly sigma. That's what's typical, is a surface charge will actually cause a discontinuity in the electric field equal in magnitude to sigma over epsilon naught. And that's actually what it is. So that's it, guys. I'll talk to you more about Gauss's law next time. But this is enough to get you started. It only gets more complicated when I add things like distributions of charge dispersed throughout a solid cylinder or throughout a solid sphere or something like that. And there's examples like that in your book and in your problems, and I'll work with some of those later. But you guys are free to go, and I'll wait for the last person to leave in case anybody has any questions.
I got a question on the extra credit because I want to show you my screen if I can.
Yeah, Trey, go for it. Let me turn it on where I'm going to stop. Does anybody
I'm
need this
Ryan.
before I stop sharing?
Yeah, I'm good.
Okay. All right. So I want to set it up where you can share. So multiple distance and share. That'll be okay. All right. Go ahead. You can share now, Ryan, I think.
Okay. Hopefully this works. Good. Okay, so did the integral, for a finite length, and and I got like basically, I don't know if I did
Yeah, that
this
looks
right.
right.
I got, yeah. Because when I did the limit, yeah, if it was at infinity, like in the infinite long,
Right.
infinite length, I got what should have been. And then I took the ratio.
Mm-hmm. Gotcha.
And
0.99.
I did.
So you found that when the distance away was about 1% of the length.
Yeah.
Yeah. So a factor of 100, and that gave you a 1% error. Is that what you were finding? Yeah, it looks like a 1%.
Well, I did it approximately because I just was like, I'm just gonna let that ratio R over L equal alpha because
Right. That looks good. Looks like, yeah, it looks like you figured it out. So you see, it's
Good.
not that hard, even though we make grandiose conclusions about infinite line charges and infinite planes. It's not that hard to reach something that looks infinite to within 1%. We literally only have to be 1 centimeter near an object
Yes.
whose end is 100 centimeters away.
So yeah, I think I got it because I was like making sure I did this integral right because I was like, wow, that all this for nothing.
Yep, you did it all right. And it's weird a lot of times when you're dealing with infinitely large things, it's harder. But in these cases, when you actually calculate the electric field of an infinite thing, it's way simpler than when it's a finite thing. The formulas get quite
I
ugly when they're
know.
finite.
Yeah, because I had to use this ugly term right here because I had to use the because I didn't have the benefit of tangent theta. I mean theta approaching pi over 2 because I was
Right.
like, I don't know what the theta is, so I'm just gonna go back into y and just use the negative L over L.
Yeah.
After
exactly. Now, did you make yours 2L long, or was it one? It looks like, okay, you made it 2L long. Let's see. Gotcha.
2L. Yeah.
That's cool.
Yeah,
Yeah,
I'm
it
just
looks like you
gonna
got it right. Anything else?
Yeah. Oh yeah, let me see the problem from the book that was kind of fun. Those discussion questions. Let me see if I
Okay.
can.
How about AJ? You got a question while he's looking for that?
Let's see. Oh, here we go. This is a
Okay.
good question. So the total electric flux out of from a cubical box of side 21.0 centimeters is that value. What charge is enclosed by the box? So we got to find what the left-hand side is.
Okay, the total electric flux out from a cubical box. Okay, so what you're saying is the flux, which is equal to charge enclosed over epsilon naught. So really all you have to do is multiply that flux times epsilon naught, and it will give you the actual charge.
Oh my goodness me, that makes a lot more sense. I was like, duh, they already gave me the value on the left-hand side. That's all I need to.
Yeah, and they
multiply
threw
by
you a
4.
curveball by giving you that 21.0 centimeters. So it made you think, oh, I gotta do something with that. Does that make sense?
Yes. Okay, I was not going to do like all the geometry.
Notice that hemisphere that you got up there at the top of the page. That electric field is only going to the right. So you can sort of pretend like maybe way out here to the left of that picture is a positive plate that's really large compared to how far away it is. And then over here on the right-hand side is a negative plate that's really large compared to how far away it is. That would create an electric field that looks just like that. Now, if that hemisphere had an actual flat side, whether it be flat on the left-hand side or whether it be another semicircle on the other side, the total flux would still be 0 because the charge enclosed is 0. Notice just as many lines go in as come out. That's what happens when you don't have a charge inside. Charges we see when we're talking about electric field lines, they begin on positive charges and die on negative charges. If they don't have a charge to hit, then they just go on forever.
This is just like a open because it's a hollow hemisphere. It's just going to be 0.
But you can cap it off with a flat plate or with a hemisphere, and you'd still get you'd actually get a closed surface. So Gauss's law would apply. Remember, Gauss's law only applies to a closed surface. The definition of flux applies to anything, but Gauss's law only applies to a closed surface.
So if I put like a surface here, like a flat disk, you still
Yep.
would be zero
Yep.
because there's no charge in it.
Yeah, and so all those field lines got to continue to the right until they hit a charge, which is off in the distance where there'd be a negative plate, maybe.
Yeah, because I don't really see a charge in there.
Yeah, remember, well, actually, I can't tell you to remember. Tomorrow you're doing a lab where you're going to actually draw electric field lines between two parallel plates. When you see that, you'll realize, oh, okay, yeah, the only way I get straight electric field lines is when two large parallel plates are oppositely charged and right next to each other. So that's why I pictured a big positive plate on the left and a big negative plate on the right.
I'm probably going to be seeing that tomorrow in lecture. Oh, so we're still going to have lecture, but we're going to do an ad hoc lab during that time.
Yeah, you'll do it with a PHET, which is a website, so you can do that.
Awesome. So I'll.
Any other
Okay,
questions,
yeah,
sir?
that's everything. No, that's all I have.
All right. Well, have a good one, AJ. Did you need anything? I think AJ might not be there anymore.
I'll see you tomorrow in the afternoon.
All right. See you. Have a good one.
Thank you.
Bye-bye.